said, we'll do trigonometric identities. So here we go. Okay, so firstly, I need to tell you what is a trigonometric identity. So I need to give you guys the definition. All right, so I will never use things that I don't define. I always try to define every term that I use. So here we go. A trigonometric identity, I'm going to underline that because that's what I'm defining in this definition, is an equation that involves trig functions and holds true for all angles theta, excuse me, such that theta is in the domain for both sides of the equation. Is in the domain for both sides of the equation. So that's kind of like a mouthful, but essentially a trigonometric identity is just an equation that holds true. Okay, it's just a true statement. All right, and it's going to hold for whatever values we plug into both sides of the equation. So here's an example of a trigonometric identity. We will show later that, in fact, sine of 2 theta, this is actually equal to 2 times sine of theta times cosine of theta. Okay, so this is an example of a trigonometric identity. Sine of 2 theta is always equal to this right side of 2 sine theta cos theta. Okay, and I will prove this later in class. Okay, I'm going to talk about this. All right, so this is an example of a trigonometric identity. All right, so first we need the really fundamental ones called the even-odd identities. Even/odd identities. Okay, so these are just going to be about sine and cosine being even and odd. So we actually have done this before, but for the sake of completeness, let me just write these out here. So we know that cosine of theta is an even function. And what does that mean algebraically? It means if I plug in the negation of an input, it's the same as the function evaluated at the input without the negation. All right, so we know what evenness means of a function. F of negative x equals f of x, or in this case, f of theta. Theta is our input here. Okay, good, and we have something similar for sine. Sine of theta is odd, which means that sine of minus theta is negative sine of positive theta. Okay, so we should know these already. I think we did this like last class or 2 classes ago. Okay, well, here is an application of this. This is why these things can be useful. So let's look at example from homework 9. Example from homework 9.
Are they always like that?
Excuse me?
Is cosine always even? It's never odd?
Yep. This equation here will hold for every single value theta that you plug into this function. Yeah, always. Okay, so here's an example from homework 9. I told you guys to evaluate sine of negative pi over 3. Okay, this is on homework 9. So what was the method? Well, you had to convert minus pi over 3 into degrees, find the reference angle, and see which quadrant we were in to see if sine was positive or negative. Well, yes, that will always work, but by oddness of sine, you can pull out this minus sign. This minus sign can come out in front. So by oddness, this is negative sine of positive pi over 3. Okay, minus sign came out front, and then minus, now sine of pi over 3 is right on our trig table. Okay, it's right there on the trig table. So this is negative radical 3 over 2. All right, and the beauty of this is that no reference angles were needed. Okay, so I hope everyone sees what I did here. I'm exploiting the oddness of sign. I can pull out a minus sign and it becomes a coefficient in front. So that's from here to here. This is oddness. All right, so that's very nice. That's a very nice property of these trig functions. Good. So on the homework, I'm going to have you prove evenness and oddness of all the other trig functions. Okay, so you'll see that on homework 10. All right, and that's not that bad. All right, let's keep going now. All right, here are now probably the most famous trig identities. So these are called the Pythagorean. So these are very beautiful identities. Pythagorean identities. Okay, sorry, just identities. Right. Okay, and here is one of them. Okay, so we have that cosine. Oh, okay. Firstly, I need to just write a note, just a quick notation note. We will, if we want to square cosine, we usually write it like this. We put the superscript in between like s and theta, okay? And similarly for sine, all right? So I just want to write that quickly. Okay, so this is just notation. Okay, so if I write cosine of theta with a 2 in between the s and theta, that's the same as cosine theta squared. Okay, this is not an identity. This is just notation. This is just how we write these things. All right, so now that that's out of the way, here is the famous Pythagorean identity. Okay, here it is. Cosine squared of theta plus sine squared of theta, this is 1. Okay, and that's quite amazing. So cosine squared of theta plus sine squared of theta is 1 for all values theta. All right, beautiful, and we will actually prove this very quickly. So this is very nice. So what you want to do is you want to draw a right triangle with hypotenuse 1. Okay, that's kind of what's going on here. So here's theta. Okay, so I encourage everyone to try and follow along with this proof because it's really not that bad. So here's theta. I'm going to construct a right triangle with hypotenuse 1. And the legs are unknown, so I'm going to call them y and x. And here's the right angle. Okay, very good. So this is a right triangle, so I can apply the normal Pythagorean theorem to this. So by Pythagoras, I know that x squared plus y squared is equal to 1 squared, which is 1. Okay, so this is just good old Pythagorean theorem. All right, so now that that's stated, now why don't we look, so what do we need to prove here? We need cosine theta plus sine squared theta is 1. So why don't I just look at that? Let me just look at these terms here on the left side. So firstly, cosine theta is adjacent over hypotenuse, x over 1. It's just x, okay? Sine of theta is opposite over hypotenuse, y over 1, which is just y. All right, I hope I'm just using the definitions of cosine and sine. Well, all right, well now we're done here. So thus, cosine squared theta plus sine squared theta is equal to, well, if cosine theta is x, then cosine squared theta is x squared. If sine of theta is y, then sine squared theta is y squared. Right? Well, what do we know about x squared plus y squared? It's 1 by Pythagoras. So we're done. We did it. So here we go. So here it is. Cosine squared theta plus sine squared theta is 1. Very beautiful.
Could you also think of it as a unit circle, like as an example, like for instance, you take the same unit circle, and if you were to get some points just to get the hypotenuse equal to 1, could you think of it like that?
Yes, yes. So
So
definitely.
cosine and sine being your x and y coordinates.
Exactly. It's the same thing. Yes, because cosine theta is the x coordinate on the unit circle. So yes, that's a nice way of looking at it. Yeah. All right. So here's the proof. I hope everyone was able to follow. So we actually do have some consequences or some corollaries. So corollary is just a mathematical term for a consequence, something that follows from a previous theorem. So corollaries, the following identities follow. So we also have these. We have that 1 plus tangent squared theta is equal to secant squared theta. And second, we have 1 plus cotangent squared theta is equal to cosecant squared theta.
Is there a difference between notation and identity? Like, what's the difference between those?
Notation is just like a definition. It's just how we write something.
Mm-hmm.
And identity is something you have to prove.
Okay.
That's something that you have to prove from prior knowledge and prior definitions. Something is just stated as fact, like, okay, this is just how we do something, but an identity is something that will follow, that you have to provide a mathematical proof for. Okay, so this will be on the homework, these two, okay? So you're gonna have to prove these on the homework, but there's really some nice hints on the homework, okay? So proofs on homework 10. So this will be a very nice exercise for you guys with hints, all right? So, I always like to give hints. They will be there for this question, all right? They're really not bad. Essentially, you just need to algebraically manipulate the first one. You don't need to draw a triangle. You just need to algebraically manipulate this guy. All right, excellent. So let's do, okay, so here we go. So let's now verify our first trig identity. So let's actually prove something. So example, verify the following trig identity. Okay, and here it is. Okay, 1 plus sine of x, 1 plus sine of x multiplied by 1 plus sine of negative x. Okay, I want you guys to prove that this is equal to cosine squared of x. Okay, now here's the strategy. Here's how you deal with these questions to verify a trig identity. You use identities to manipulate. Okay, you use known identities, You use known. So previously known, use known identities to manipulate the left side. The left side until it matches the right side. That's what you do. Usually, this is a very good strategy, okay? So you start on this left side, you manipulate it, you use identities, and you transform it and prove that it's equal to the right side. All right, good. So let's actually do this together. So firstly, I see a sign of minus x here. Sign is odd, so I can pull that minus sign outside of the function. So the left side is equal to 1 plus sine x times 1 minus sine x. Okay, so all I did here was just bring this minus sign and the input outside as a multiplier, as a coefficient, right? That's by oddness. Good. Now multiply this out. Okay, this is actually a difference of two squares in reverse. So this is actually, if you just multiply this out, you will get that this is equal to 1 minus sine squared x. Okay, so just multiply these expressions. Okay, now what's the goal? We want to show that this is equal to cosine squared of x. Well, this is equal to cosine squared of x by the Pythagorean identity.
When squaring, you don't add the 2 to x because x is just part of the trig function.
I wasn't able to hear you that clearly. What did you say?
When you square the sine of x, you don't put a superscript on x because it's part of the trig function?
Right, because I'm not squaring x, I'm squaring the sine function. It's not x squared, it's sine squared. Okay, so does everyone see why one, actually, can someone explain to me why 1 minus sine squared is equal to cosine squared? Maybe someone can just explain that to me.
If you were to equal them together, so 1 minus sine squared of x equals x squared, you just have to move the sine squared x to the right. And you'll just get sine squared x plus cosine squared x equals 1.
Right, good. That's one way to look at it. I would look at it a little differently. I know that cosine squared plus sine squared is 1. This is a true identity, but you can just subtract sine squared from both sides. Cosine squared is equal to 1 minus sine squared. Yes, which is essentially what you said. So you're just literally just bringing a sine squared over to this side. All right, so I hope that's okay with everyone. So please let me know. And just note that we're done because we wanted to show that it's cosine squared and we did it. So, you're finished. All right, here's another example. Okay, show that sine of x times, sorry, I feel like I'm writing very sloppy today. Show that sine of x times cosine of minus x times secant of x is equal to sine of x. Okay, so as before, we start with the left-hand side, okay? And we algebraically manipulate that. We use known identities until it matches the right side. Okay, so let me start with that. Left side equals, okay, if you see a cosine of negative x or something with a negative x input, that you should automatically appeal to evenness or oddness. Okay, so using evenness or oddness, can someone tell me what this left side becomes?
So you'd have sine of x times negative cosine of x.
Why negative cosine of x?
Well, since it's, oh no, you're right. No, it would just be cosine of x because it's an even function.
Yes, good. So cosine's even, so the negative x in the input can just be deleted. It's the same thing as cosine of x. Okay, so by evenness of cosine, this is the same as sine of x times cosine of normal x times secant of x. Okay, so that's by evenness. Evenness. Good. All right. So we're almost done here. Now you want to just kind of unpack your definitions. Sine and cosine, that can't be changed. But secant can be changed. So what's the definition of secant?
Inverse of cos.
Right. Yes, exactly. It's the multiplicative inverse of cosine. Right. So it's 1 over cosine. And, this is a very nice thing. This and that will cancel. They will reduce to 1. So we're just left with sine of x, okay? And that's what we set out to prove. That's the right side. So it's quite nice, and you know, these are nice, interesting problems to work on, okay? All right, so any questions? All right, so yeah, you do a question. No, okay. Yeah, so you'll have a lot of practice on the homework with these things, and we're going to do some more later. We're going to do more trig identities later in class. Okay, the next set of identities are the sum difference identities. Sum slash difference. Sum slash difference identities. Okay, and these identities, they're not as aesthetically pleasing as the Pythagorean identity, but they are very useful. Okay, I will give them that. They are extremely useful in some situations. They're just kind of, they're not as nice looking, in my opinion. All right, so here we go. So firstly, just a quick bit of notation. We use the Greek letters. We use the Greek letters, alpha, which is written like this, and beta, which is written like that. Okay, so this is more of a historic, conventional thing, what mathematicians have been doing for years. For some reason, in this scenario, we use the Greek letter alpha and beta. Okay, good. So let's start now. So cosine. Cosine, here we go. For two angles, alpha and beta, we have, okay, we have the following. Cosine of alpha plus beta. So we're going to be interested in taking cosine of a sum. Okay, what does this equal? This is cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Okay. We also have one for the difference. Cosine of alpha minus beta. We have a similar identity. That is cosine alpha times cosine beta plus sine alpha times sine beta. Okay. Yes, I'm just making sure I wrote them correctly. Yes, so these are them. Do not memorize these. It would be silly to do that. You can always just like look back on your notes and whatnot, okay? So this is how so these are them, but now let me just highlight why they're useful. Like, why do we care about them? Okay, so these are especially useful in finding exact values of trig functions at unknown angles. At unknown. Okay. And when I say unknown, I mean like the angle is not on our trig table. Okay, we know the trig table. We don't need any special tools for that. But sometimes these formulas will help us to find an unknown angle. And here is a very nice example. All right, so this is actually quite nice. So find the exact value of cosine of 75 degrees. Okay, firstly, 75 is not on our trig table. And moreover, 75 does not make a reference angle that's on our trig table. So we can't use previous methods to get at this value. Okay, so here is the deal. The strategy is to write 75 as a sum or difference of known values, such as 30, 45, 60, 90, 135, etc. And why would we do that? Well, because we have values for these guys, these 30s, these 45s, 60, 90, 135. Okay, so we need to think now, how can I write 35 as like a sum of these pieces here? Let's think for a second. 75 equals something plus or minus something. So can anyone look at these numbers here and kind of cook up a way to get 75 using plus and minus, plus or minus?
30 and 45?
Yeah, excellent. Yeah, so 75 is equal to 30 plus 45. That's the deal. Excellent. So that's what we will use. So thus, cosine of 75 is literally the same as cosine of 30 plus 45. Okay.
So you'd want to use the unit value. I'm sorry. How do I say? So basically, you would want to use the unit circle degrees that we already know, like
Yeah,
30, 45, and etc.
exactly. You use those as your building blocks to get at this unknown value. Yes. So look at what we have here. We have cosine of something plus something. Doesn't that look exactly like cosine of alpha plus beta? Well, it is. It's just with a specific value for alpha and beta. So we make this alpha, this is beta. Oh, whoops, I wrote alpha twice. That's alpha and that's beta. Okay, and now you just use the formula. So this is equal to cosine of 30 times cosine of 45 minus sine of 30 times sine of 45. This is directly from the identity here. Okay, so directly from this guy.
Where does sine come from in that? I mean, isn't it just cosine? But I mean, I know that's part of the identity, but where does sine come from in that?
Okay, so unfortunately, the proof for this, the proof for this angle, for this sum formula is actually quite involved. So we're not going to prove it here.
Right.
I know it's weird. Why does sine show up, right? I feel you on that. I don't. It's weird, but you can look in the textbook for a proof. I don't like the proof in the textbook, but you can probably find some other proofs on like YouTube or something. Yeah, but I know it is kind of wild. Okay, and the whole point of writing 75 as 45 and 30 was because we have values for each of these guys. That was the whole point. So now you go to your trig table and you just fill out these values. That's root 3 over 2. The second one is root 2 over 2 minus that one's a half, and that's root 2 over 2. All right, and this is just so beautiful. we have an exact value, this will be radical 6 minus radical 2 all over 4. Okay, so it's quite nice. So we actually have a nice closed form for cosine of 75, all right? So you'll have practice with these on the homework. It's really nice. Okay, so we just have cosine. We will also do this the same thing for sine. So sine now. Here we go. Sine of alpha plus beta. Okay, this one's a little different, so I just have to be careful that I don't mess this up. Okay, sine alpha cos beta. So sine of alpha times cosine beta. Yep, plus cosine alpha times sine of beta. Yes, okay. Good. Next one is just with a minus sign, alpha minus beta. So let's do that one. Sine of alpha minus beta. Okay, this is sine alpha times cosine beta minus cosine alpha times sine beta. Very good. Okay, got it. Got it. Okay, you can see that these look very similar to the cosine ones, but they are different. They are different. All right, so just make sure you look very carefully at which one you need when you're doing these types of questions. All right, so here's an application. Again, we're going to evaluate a trig function at an unknown value. So evaluate sine of pi over 12. Okay, again, pi over 12 is not on our trig table. It's not 30, 60, 90, 45, one of those nice angles. Okay, in fact, pi over 12 in radians is equal to 15 degrees. Okay, so you can see immediately it's on our trig table. Okay, so now we need to write 15. So here's the strategy again. We need to write 15 as a sum or difference of known angles. Again, when I say known angles, I mean we need to write it as a sum difference of 30, 45, 60, 90, and so on. Okay, so this is not bad. You know, indeed, 15 is actually equal to 45 minus 30. So maybe you would guess, maybe you guys had this in mind even before I wrote it. This is the way to do it. You write 15 as 45 minus 30, and now you just kind of go through the computation. So sine of pi over 12 is the same as sine of 15 degrees, which is the same as sine of 45 minus 30. And now here is alpha, and here is beta. So we're using the difference formula. We're using the second bullet point right here, using the difference formula. Okay, so by the difference formula, this will be sine of 45 cosine of 30, right? It's sine alpha cosine beta, yep, minus cosine 45 sine of 30. Very nice. And you actually get the same answer from the previous example. So this will be root 6 minus root 2 over 4. Same answer. All right, so any questions on the strategy, on the thought process, on anything. All right, so we'll move on now. All right, now we're going to do the double angle formulas. Okay, here they are. Here's the first one. Sine of 2 theta is equal to 2 sine theta cos theta. Okay, this is the one I wrote out in the beginning of class, if you remember. Second one, we have another one. Excuse me. We have cosine of 2 theta. Wow, this one looks a little different. This one is cosine squared theta minus sine squared theta. Okay, so why are these called double angle formulas? Well, look, we're taking sine of double the angle theta. We're taking cosine of double the angle theta. That's why they're called double angle formulas. All right, good. I'm going to prove 1, and you guys are going to prove 2 on the homework. Okay, so here's proof of 1. Proof of 1. So here's the trick. You use, this is so awesome. You use this identity, sine of alpha plus beta, with the values alpha equals beta equals theta. That's what you do. So here we go. Sine of 2 theta is equal to sine. So do you guys agree I can rewrite the input of 2 theta as theta plus theta? Why not? I can rewrite 2 theta as theta plus theta, and now you use the sum formula. Okay, now use sine of alpha plus beta identity. So it's really quite nice. Okay, so here we go. This comes out to, so you just have to apply this identity. Right, so it's sine theta cosine theta. We're using sine theta cosine theta plus cos theta sine theta. Right. Well, yeah, plus sine theta cosine theta. Okay, and look here that these are like terms. Okay, these are the same. So this is just 2 of them. This is 2 sine theta cos theta. And that's it. That's what we set out to prove. That's the right side here. All right, so any questions on this proof? It's basically an application of the sum formula for sine. Okay, good. Proof of 2 is on homework 10. Very similar. You're going to do the same thing, pretty much. And I do supply some hints, okay? Alrighty. Okay, let's do another verification of a trig identity. Okay, verify the following. Verify that sine theta plus cosine theta quantity squared is equal to 1 plus sine of 2 theta. All right. So as before, the strategy is to always manipulate the left side. Manipulate the left side until it matches the right side. Okay, so the left side is as follows. So if you actually square out this parentheses here, you will get sine squared theta plus 2 sine theta cos theta plus cosine squared theta. So that's what you get when you multiply out this set of parentheses, okay? You get sine squared theta plus 2 sine theta cos theta plus cosine squared theta. Okay, now, what if I bring these two terms together? If I just move them next to each other? Well, look at this. I'll have sine squared theta plus cosine squared theta plus 2 sine theta cosine theta. Okay, so look at that. Let me maybe change the highlighter color here. And we have that. Sorry, my video. Okay, very good. So does anyone see how I can rewrite these two highlighted portions? This is something nice, and that is something nice. So let's maybe think for a second, maybe look for earlier in the notes. So any ideas? I want you to rewrite this yellow highlight and this green highlight using some previous stuff.
The right side of that, the green highlighting, wouldn't that be sine of 2 theta?
Yes, exactly. This 2 sine theta cos theta is literally the right side of the double angle formula. Yes, it's sine of 2 theta. Very good. Okay, excellent. And what do we know about sine squared plus cosine squared?
Is that 1?
That's 1. Yeah, that is the Pythagorean identity. Whoa, I don't want that. Hold on, sorry, just the colors got messed up. Yes, sine squared plus cosine squared is 1. That's the Pythagorean identity. There you go. And we're done.
I'm sorry, can you scroll up just a little bit for? Thank you.
Yeah.
I have a question.
Yeah.
Can you go over how you got 2 sine theta cos theta in the middle of?
Sure. Yeah. So, yeah, so this is just like multiplying out polynomials. So what I did here, I can I can call this x maybe, and I can call this y. So this is the same as x plus y squared, which is the same as x plus y, x plus y. And now this is just like multiplying out like two polynomials. You do this, you do that. So it's x squared plus xy, then this plus yx, and that plus y squared. You get it? And then this is 2xy, but x is sine theta, y is cosine. Yeah, that's pretty much the deal.
Thank you.
Yeah, no problem.
Like the whole expression is like a set.
The
To be
whole,
squared, I mean, like to be multiplied. It's like a group set.
it is a polynomial in a trig function, maybe I would say.
Okay.
A set is something, is a different word for something else in math. But yeah, it's pretty much you're multiplying two polynomials. It's the same procedure. All right, so that's quite nice. All right, so let's keep moving. So we're actually making really good time here, which I'm happy about. Okay, next is the so-called power reduction formulas. So let's now talk about those. power reduction. Okay, and you'll see why we give it this name in a second. You'll see why we call it the power reduction formula. All right, so here's the first one. So we have that sine squared theta is equal to 1 minus cosine of 2 theta over 2. Sorry, it's a little sloppy. So it's 1 minus cosine of 2 theta over 2. That's the first one. Second one, cosine squared of theta. This is similarly 1 plus cosine of 2 theta. Sorry, I'm having a hard time writing today, excuse me. Over 2, okay? All right, why are these called power reduction formulas? Well, the power of sine squared, the power on the left side is 2, but the highest power on the right side is 1. So we have reduced the powers from 2 to 1. And similarly with the second guy, we reduce the power of 2 to a power of 1. This will be very useful in calculus 2. Okay, so hopefully some of you guys will be going on to that, and these will become very handy when you're taking the integral of sine squared and cosine squared. Okay, all right, so here is an example. Here's an example. Oh, okay. All right, here's an example. Okay, right. Cosine to the fourth power. Cosine of x to the fourth power into an expression with all powers being 1. Okay, so I'm giving you cosine to the fourth power. I would like now to write an equivalent expression, but every exponent or power is 1. All right, so here's how you do it. Cosine to the fourth x, you guys will agree, this is the same as cosine squared of x squared. Okay? Now, cosine squared of x squared. I use now the power reduction formula on the part inside the parentheses. I use this guy on the inside of the parentheses. So this is equal to, so here's the power of 2. That just stays, but I replace the parentheses with its equivalent expression of 1 plus cosine of 2 theta over 2. This is 1 plus cosine of 2 theta over 2. Okay? All right, very good. So now you can just algebraically manipulate this. So you can bring out the 1 over 2 squared as a 1/4. And now you just can multiply, you can square the numerator. This will become 1 plus cosine of 2. Oh, sorry. So this is in x's. That should be in x, 2x. I'm sorry. Cosine of 2x. Okay, so this is now 1/4 times 1 plus, okay, sorry. Okay, so the 1/2 squared came out in front. Now I just need to square the numerator. if I square the numerator, I get 1 plus 2 cosine of 2x plus cosine squared of 2x. Okay. Okay, we're not done yet. Look at the prompt. We need all powers being 1. We still have a power of 2 here. So we need to now again apply the power reduction formula to that last piece. So let's do that. This will be 1/4 times 1 plus 2 cosine of 2x. Now, cosine squared of 2x will be 1 plus cosine of 4x over 2. So any questions here? I think maybe you should have a question. Why is this 4x when this was 2x? That became a 4x.
Because the formula asks for 2x, so 2 times 2x, it's 4x.
Yes, exactly. So when you apply this power reduction formula, you need to double whatever theta is. So if theta is 2x, I must double it and make it 4x. Very good. Okay. So if you're doing this now in pre-calc, you will be very familiar with it when you do it in Calc 2. You're going to have to do the same exact thing in Calc 2. So will be very useful in Calculus 2. So I really hope that some of you guys take that. That's a very beautiful class, and I personally will probably be teaching it over the summer for purchase. Okay.
Could you just repeat the part why we have to double 2x again? I'm sorry.
Yes. So basically, I need to apply this formula, this highlighted guy, to the angle 2 theta, because that's what I have here. I have cosine squared of 2x. Okay, so when you go from here to here using the identity, when you actually apply it, you must double whatever theta is, whatever the input is.
Got it, thank you.
Because look, it's 2 theta. Yeah, so if I double 2x, it becomes 4x. Good. All right, so you will have to do the same thing for sine to the 4th power on the homework. Okay? But this will be the same. It's the same thing. All right, let's keep moving. Okay, next we have the half angle formulas. Half angle formulas. Okay, these are okay. So the first one is sine of alpha over 2. We have this. We have this is equal to plus minus the square root of 1 minus cosine of alpha over 2. Okay, and we have the second one for sine, for cosine. Cosine of alpha over 2. This is plus minus big square root of 1 plus cosine alpha over 2. Okay. Okay, and these you can prove immediately from the power reduction formulas. All right, maybe you can see the connection. You let theta be alpha over 2 in the power reduction formula, and then you have to take a square root of both sides. That's the proof, essentially. So these follow immediately from the power reduction formulas. All right, so you can see the similarities. All right, let's do an application. Example, find the exact value of sine of pi over 8. Okay, how do I use this formula? I need to realize pi over 8 as something over 2. Because look at what this half angle formula calls for. It calls for sine of something over 2. So I need to rewrite pi over 8 as something over 2. And hopefully that something is a known value. It's one of our nice trig values. All right, so essentially this is how it works. You let alpha equal pi over 4. Then pi over 8 is equal to alpha over 2. So do you guys see that essentially pi over 8 is equal to pi over 4 divided by 2? And now I'm of the right form to use the trig identity. All right, so let me know if that's okay. Thus, sine of pi over 8 is the same as sine of pi over 4 divided by 2. Okay, and now I use the half angle formula with alpha being pi, whoops, don't want to erase it. I use the half angle formula with alpha being pi over 4. See, I have an alpha, there's my alpha, over 2. It matches the identity perfectly now. Good. So now you just apply the identity. There's not much to do now. So this is equal to plus minus big square root of 1 minus cosine of pi over 4 over 2. Okay, this is from the identity half angle formula. And now this is equal to the square root of 1 minus root 2 over 2 divided by 2. And that's all underneath the square root, this fraction. Okay, you should be noticing now I got rid of the plus minus, it's just a plus. Reason being, take the positive root, since sine is positive in the first quadrant. Since pi over 8 is in quadrant 1 and sine is positive there. So I have rejected this negative root. I just took the positive one because we're in the first quadrant where sine is positive. All right, so any questions here? So this one can be a little tricky, I think, but just please let me know.
So you'd first have to just verify which quadrant you're in.
Say that again?
Would you just have to verify which quadrant you're in?
Yes, you need to look at the input and see where that angle lives. What quadrant does pi over 8 live in? And that's, I think, I don't know what degrees that is, but it's in the first quadrant for sure. Yeah.
If there was a negative, then it would be in the second quadrant?
No, if it was negative, you need to travel clockwise and see where you.
Oh, yeah, you're right.
Oh, I see what you're saying. If we were in the third or fourth quadrant, you would take the negative root.
Yeah.
The negative square root, because sine is negative in the third and fourth quadrant.
Got it.
All right, so that will do it for identities, okay? So what I presented to you guys are perhaps the most important or the most popular trig identities, but there's so many more out there, but they're kind of exotic and obscure. So I gave you guys the most popular ones. All right, so now let's kind of shift gears. Let's talk about solving trigonometric equations. Okay, so let's talk about the definition. What's the definition of a trigonometric equation? Okay, definition, a trigonometric trigonometric equation is an equation involving trig functions, as the name suggests. Okay, we wish to solve these equations for the variable theta. Okay, so before we get into this, I need to recall periodicity. Okay, recall periodicity. So remember, the sine and cosine functions are periodic. So remember, sine of theta is equal to sine of theta plus 2 pi k. And 2 cosine of theta, similarly, is equal to cosine of theta plus 2 pi k. Okay, so you should be asking me now, what is k? K is just going to be some integer, okay? So k, so where k is plus minus 1, plus minus 2, plus minus 3, and so on forever. All right, it's one of the, it's just any integer. So this follows from periodicity of cosine and sine. All right, hope that's okay. So this is going to be important. So for example, if if we know that theta satisfies some equation, if we know that theta satisfies cosine of theta is equal to some number a, let's say we know this, we know that theta satisfies this equation, okay, a is a number, then also theta plus 2 pi k also satisfies it. In other words, cosine of theta plus 2 pi k is also equal to a. Okay, and this follows directly from periodicity of the cosine function. If I add 2 pi k to theta, the value of cosine is unchanged. So if cosine of theta is a, then cosine of theta plus 2 pi k will also equal a. All right. So any questions? This is kind of like a fundamental concept here. Alrighty, I guess everyone's good then. So here's an example then. Find all solutions to cosine of theta is equal to 1/2. Okay, good. So from our earlier work, we know that theta equals pi over 3 and theta equals 5 pi over 3. Solve this equation. Okay, so this goes back to our work on with reference angles. You take cosine of pi over 3, and if you take cosine of 5 pi over 3, you will indeed get positive 1/2. Okay, you can verify that for yourself. But these are not the only solutions. We have an infinite family of solutions. But by periodicity, all solutions are theta equals pi over 3 plus 2 pi k, and theta equals 5 pi over 3 plus 2 pi k. Plus 2 pi k, and here k is any integer. Okay, so this is just like I did up here. If cosine of theta is equal to capital A, then I know that if I add 2 pi k to theta, that also solves the equation. That's by periodicity. Well, you do this now with theta's pi over 3 and 5 pi over 3. So any integer you pick, 1, -1, 2, -2, 3, and so on, plug that in for k, that will be a solution. So we have infinitely many solutions. We have an infinite family of solutions. Okay, so hope this is all right. I'm not really hearing from anyone tonight or right now, but hopefully this is okay. All right. Okay. So you won't always have to do this plus 2 pi k business. So yeah, maybe I'll type this. Okay. So if the equation, if the question asks us to solve the equation over the interval 0, 2 pi, we need not add plus 2. We need not add plus 2 pi k to our solutions. Okay, so sometimes you will be given a trig equation and it will just tell you to solve the equation over the interval 0, 2 pi. And in that case, you're just looking for solutions that live inside of the interval 0 to 2 pi. In such a scenario, you do not, in fact, it would be wrong to add this 2 pi k thing at the end. All right, so here's an example. Solve 2 cosine of theta minus 3 equals -5 over the interval 0 to pi. Okay, so this is the same as the previous question, kind of, except now we're only looking for solutions that live inside this interval, okay? All right, so basically you need to just isolate the trig function. So you add 3 to both sides. Look at 2 cosine of theta is equal to -5 plus 3, which is -2. Now divide both sides by 2. You will get that cosine of theta is equal to -1. Good. Now we know when cosine is -1. That's when the x value on the unit circle is -1, and that's at pi.
Where did you get -2 from?
I got -2 by adding 3 to both sides of the equation.
Oh, okay. Gotcha.
And cosine of theta equals -1. That's precisely when theta is pi. So we know cosine of theta equals -1 when theta equals pi. Thus, the answer is that. Okay. Now just note, if we added 2 pi k to this value, we would step outside of the interval 0 to pi. That's why we don't do it now. We just keep that one value of theta. All right, last thing. Yeah, last thing. Okay, we're gonna now just talk about very quickly trig equations in quadratic form. Last thing. Okay, here we go. Example. Solve 2 sine squared theta plus sine theta equals 0 over the interval 0 to pi. 0 comma 2 pi. Okay, so this is the strategy. So you guys can see this is like a quadratic equation, but the variable is sine theta. So here's the strategy. You have to let x equal sine theta. Strategy is to let x equal sine theta and rewrite. Okay, if I let x be sine theta, this equation becomes 2x squared plus x is equal to 0. Okay, now you solve the quadratic. And now you solve this quadratic, which we know how to do. So we're always trying to find methods from earlier stuff that we did. And here we go. So how do we solve this guy? We can actually solve this by GCF. You can pull out an x. This is x times 2x plus 1 equals 0. Use the zero product property. So this gives us solutions as x equals 0 or x equals -1/2. Okay? By the zero product property, you set each factor equal to 0 and solve. We've done this before. Now, we're not done yet because x equals 0 is not our answer. X is sine theta, so you need to go back and substitute in. So now, substitute back. Substitute back in for sine theta. Okay, if x is 0, that means that sine of theta is 0. And if x is negative 1/2, that means that sine of theta is equal to negative 1/2. Now you solve these two trig equations. And that'll be it. Okay, so solve the first one. Let's just look at this guy. When does sine of theta equal 0? Essentially, we're asking ourselves at which angles on the unit circle is the y value 0? And that will be at 0 and pi. So the first one is theta equals 0 and pi. That's this guy. Second one, you will get theta is equal to 7 pi over 6 and 11 pi over 6. And that's it. Those are the solutions. We don't add 2 pi k to this because the prompt was just to solve over the interval 0, 2 pi. So we're done. So I hope you guys see these two solutions came from this guy, and these two solutions came from that guy.